have the same. The number of bits. The number of populations. Yeah, 2 to the M.
For every it should be n. So so like it represents whether a predicate is true on
Yeah.
value.
Yeah.
So either it's true or not, it's both, then it's not satisfiable. And so like you have like predicate 1 is the first bit, 0, 1, predicate 2 is the second bit, 0, 11, through n. And so that's like a very unique combination that we already.
The most important thing is to make sure you don't have too many corresponding ones in the smaller one, because if you like run, if you pick from B instead, and like A only has 3 elements of that same string, and you have like N in B, you lose the game, because like they could just keep picking from B, and then you like won't be able to find corresponding one on A. Yeah. So yeah, but you have to construct like that tree and then like check how many elements actually have this thing, and you take the minimum of like how many there are and like enter something, so you can bound it by the rounds of the game. Because like you can pick the same bit string like n times in the game if there were at least n an A. Yeah. But I got all like I had so many like mapping functions that I got all confused, like I didn't work right in my sequential round.
Do we interrogate?
Yeah. I think I figured out like the simplest way to do it, but it's still like annoying. I also didn't write it in time. I figured it out like this morning. So
What's something?
Yeah. It's not my
I'm not convinced. Like, I think, yeah, like, I think the intuition is correct, but I'm not sure it's correct. Yeah, I didn't know how to set up like the intuition is probably there. So it's not. I wanted to have like here's operators, here's how you staff constructed.
Yeah.
You could modify the formula, like reserve the variant. No, then I tried to like reduce them over. I'm only gonna do it for all in a day. Yeah. Like 2 hours, it is a stat, so like 2 hours of people can say that.
Oh, maybe Dan's gonna show us the answer.
Oh, well, you're talking about the homework?
Yeah, 1C and 1D.
Please.
What was the question in 1 second?
Satisfiability is decidable for a 0 empty vocabulary.
And for unary predicates, but not binary.
Right, I need to post a solution. So I have a solution without arrange for expressing games.
Yes, we're very interested in that.
It takes some work. So what I'm going to do, I'm going to email it to class. What about that? It's actually easier to prove as a warm-up. If you consider a language without equality. So if you don't have equality, all you can say about the relation is if it's empty or not empty.
right.
So you have n relation. Sorry, you have I have n relations. So there are 2 to the n possible intersections of these relations with the others, or these are complement. For each of them, you can check, is it empty or is it non-empty? Yeah, and this is all you can say. So if you have a formula, if in order to check satisfiability, you only need to iterate over models where each of these combinations of intersections is either empty or non-empty, or how many? 2 to the n combination. And for each of them, check your formula, if it's true or false.
Why do you have two different combinations?
Because you have two to the nth possible cells. And each of them can be empty or non-empty. Let me actually write this down. So I realize this is not visible on Zoom, and I apologize for this. Zoom is an entire saga. Let's see how we are doing on markets. I forgot to bring markets. So let's suppose we have vocabulary with three unary relations, A, B, and C. So then what can we say in this logic? What can a sentence say? So we can say something like this, without equality. It can be intersected B, intersected not C, is non-empty. Or, I mean, the same sentence can also say or A intersected not B intersected C is empty. It's a possible sentence. Is it clear how we write this in terms of the logic? Yeah, a non-empty, we say there exists X such that A of X and B of X and not C of X. And now I want to continue to say or this is empty. So it's not the case that there exists X such that A of X and not B of X and C of X. So more precisely, for any two models, if all these 8 possible cells, because there are 8 such possible cells, where you take the intersection of either the relation or its negation, if for each of these 8 possible cells, either both models are empty or both models are non-empty, if you have 2 such models, then whatever your sentence you have, it's either true in both or it is false in both. Yeah, because this is all we can say, emptiness or non-emptiness. So therefore, if this sentence has any model, then it has a model in which these cells are either empty or have one element. This is all we can distinguish, it's one element. So there are 2 to the power n cells. I call them cells, maybe you know different ways. These complete intersection. In this case, there are 8, and with n is 3, so there are 2 to the n possible cells. So how many different models do we need to check before, in order to decide if phi has a model or not? And remember, we only care about models where each cell either has one element or has 0 elements. So how many cells, how many models do we need to check? To do that? To do this. So we need to check 2 to the n models. Why? Well, there are so many cells, so let me actually enumerate them. So we have not A, not B, not C, not A, not B, C, all the way up to ABC. One model would be the following. This is empty, empty, empty. Another model is this is empty, empty, this is 1. The other one is empty, empty, 1 and 0, and so on. For each combination of empty, non-emptiness of each of these cells, there is a model that that sentence could make that sentence true. And this is how we check satisfiability. Now, suppose, I did assume that we do not have equality. If we do have equality, what changes? What can I check about such a cell?
How many elements you have?
how many, but not, it's a little bit subtle. If I only have k variables and the formula only has a finite number of variables, I look at how many it has, k. So then what can I check about such a cell?
There are k different ones that satisfy it.
There are k different ones. I can check anything about this cardinality, but only up to k. I can check maybe this cell has either 7 or 9 or 15 or more than 20 elements. That's what I can check, but I cannot extend beyond k. So now, with the same argument, now I need to check for each cell a number of elements that goes up to k, because this is how many distinctions I can make. Proving this rigorously requires some sweat. But it is immediate if you learn about arithmetic games. And again, I hope we have a lot of fun. First of all, I should tell you, don't worry about the accuracy of your homework. Do your best effort, try to learn, and have fun. I'm not going to nitpick you on missing comma as a proof. I just want to make sure that you're submitting the homework so you keep up, and you're also having fun looking at the problems. But if you dug deeper and read about arithmetic games, that is an interesting topic to learn about. And at the end of this quarter, as I mentioned, we will have a project or reports presentation, I don't know how to call them, where each of you will pick a topic and write a short report and give a short presentation for probably 10 minutes. Arithmetic games is one possible topic. And once you understand how arithmetic games work, it's so easy to prove these statements. And the second kind of games are called pebble games. There is a subtle distinction, and that can also be a topic for a presentation. I just added a new one, but it takes me some time to think about these and try to describe them. Yes?
Do you have office hours?
Send me an email, and I'm happy to meet with you. I didn't schedule a regular office hours. I'm going to ask you to come to the Simons Institute.
Are people, is it still an active area of research, like using EF games to prove inexpressibility, or is that been, I don't know?
It's considered to be a tool that you should be able to use, and I mean, people will say it's obvious you just use arithmetic games, and sometimes for me it's not that obvious. I'm not super familiar with arithmetic games, so but for people who work on this, it's clear how to use arithmetic games.
I guess, have people already mapped out what is and isn't expressible with that technique?
Yes. So with arithmetic games, you can the spoiler can win if and only if the two structures are indistinguishable by a first order logic formula with k variables, where k is a number of pebbles in the game. A mouthful, but it's exactly known what they describe. And the proof is not that difficult. It's quite insightful. And the pebble games, they go infinitely number of steps. So they are about recursion. I think your question, Connor, is about games in general. Beyond arithmetic games and pebble games, there are other kind of games for different kind of logics, for different kind of setups. There is a game for 3D composition, which I don't understand, but Jörg Gottlob worked on this, which brings me to the topic of our lecture. 3D composition is something that I was planning to describe, but maybe we'll go very quickly over it. I'm not sure whether we can get to it. And one way to describe the three ways is by using certain games, the rubber and Warden games, something like this. And I don't know that topic, but if you're interested, it might be a fun thing to read. Sorry, you had a question here. Did you have a question? Okay. Good. Can somebody please do me a favor and check on Zoom if you see a clean picture of the screen without, yeah, because what happened last time, it recorded The screen is covered by the Zoom window showing all the participants. So you can't actually see the slide. It's embarrassing. Also, the sound is pretty bad. So I'm going to try to stay closer to my computer so the sound is recorded better. Good. Any more questions before we start? Cool. So let's talk about query evaluation. This is a section where we stopped last time. And I want to dig deeper into the basic question, what is the complexity of evaluating a query? A conjunctive query, or more generally, a first order logic query. So we already know what the data complexity is. Quick question to you. What is the difference between data complexity and combined complexity? What is the data complexity of query evaluation? Yes?
The data is how long it takes to evaluate the query with respect to the data growing, the size of the data growing.
Exactly. It's how long it takes for the query to evaluate when the data grows. More precisely, the query is fixed. And we ask the question, what is the complexity of evaluating the query when the only input is a database? We are interested in the complexity and the size of the input database. How will you describe the combined complexity? Yes, Connor, do you want to try?
Complexity as the data grows and as the query grows.
Perfect. So now both the database and the query are part of the input. They both can grow. And we care about the complexity measured in terms of both. It turns out, for reasons that nobody can fully understand, that the combined complexity in all cases we know, it's the same as the so-called expression complexity, where the database is fixed and the query grows. So we already know that the data complexity is very low. It is in AC0, which means it is in polynomial time and it is in log space. But the correct complexity is a very, very low complexity class called AC0. We didn't discuss expression complexity or combined complexity for first order logic. We will do this by discussing the complexity of conjunctive queries, CQ here. And we will also discuss this will allow us to close the gap and discuss the combined complexity for first order logic, which we did not discuss yet. So the topic will be query evaluation for conjunctive queries. Yeah, the simplest and most elegant queries. And it turns out that evaluating conjunctive queries is the same as looking for homomorphism. There are three different ways to look at conjunctive queries, and I describe them here. At the top is a typical conjunctive query. We have a conjunction of atoms, R and S and R. This is with self-joins. I did not show you the head variables because for this slide they don't matter. But in general, it matters if we want to return all the variables. Then we call it a full conjunctive query. Then we get a huge result. Or we want to essentially quantify all the variables. Then we only care about whether this query is empty or non-empty. That's called the Boolean query. But for this slide, it doesn't matter what the head variables are. To this conjunctive query, we associate a so-called canonical database instance. It's a database instance that is obtained directly from the query. Every atom in the query becomes a tuple, and that is our database instance. I also gave names to the attributes, but you can ignore them. And the third equivalent presentation is a hypergraph. What is a hypergraph? Do you remember what a hypergraph is?
Hypergraph is like where the edges can contain more than 2 nodes, I think.
Perfect. A graph is every edge has 2 nodes. A hypergraph, every edge can have an arbitrary number of nodes. So here is how I view the query above as a hypergraph. There is a hyper edge for XYZ. Here is my hyper edge. Another hyper edge for UVW, that would be that. And many binary hyper edges for the S's. And we also want to label these hyperedges with the name of the relations, with R or S. Yep. So these are three different presentations of the same concept of a conjunctive query. We will switch back and forth between them. Okay, good. So let's talk about homomorphism, which is a fundamental concept in mathematics in general, and for conjunctive queries in particular. Fix two conjunctive queries. I didn't know how to write them concisely. So just imagine that each X here consists of multiple variables, and these names, they can be the same or they can be distinctly S's and R's. Yeah, two conjunctive queries. A homomorphism from the second one to the first one. We always go from the second one to the first one for a reason that will become clear next week, next lecture. So a homomorphism from Q prime to Q is a function that maps all the constants in Q prime and the variables in Q prime, maps the constants and variables to the constants and variables in Q, such that, first of all, the constants are mapped to the same constants. You can't map it anywhere else. The variables, you can map them to either variables or constants, but with the following restriction. For every atom in the original query Q prime, you must find another atom in Q such that the homomorphism applied to the variables of the first atom is exactly what you had in the second atom. Exactly those variables or the same constants. And moreover, the name should be the same. This S and this R must be the same relation name. And the last condition is that the homomorphism must map the head variables to the head variables. Yes?
I forgot how we were defining constant here. Or are we just, is it like a function with only,
With no argument.
yes.
So a constant, you can think of it as a function with no arguments. But for conjunctive queries, we actually never have functions. So I think of a constant more like an alternative to a variable. Whenever we write an atom, we can list there either constants or variables inside the atom name.
Okay.
I hope I'll have an example. Yeah, I have an example on the next slide. And if you're familiar with graph homomorphism, then this is exactly the same notion. If Q is a graph and all these atoms represent the edges, and similarly for Q prime, then a homomorphism between graphs is exactly a homomorphism between the corresponding queries. Yes.
Does H have to map the like YJ variables to the same length instead of XI, or can it be a different length?
It's a good question. So the length is preserved by definition. The function only maps single variables to either single variables or constants. And when we apply it to a tuple, then we apply it to each component, and we, by definition, we preserve the length.
So as a follow-up then, so should I think of a homomorphism as basically making a new query that's more constrained, because you can only add more, I guess, like atoms to the query. You can never remove one, because then you'd be missing the second condition would be violated.
It's a very good observation. In some sense, let me put it this way. Suppose I start with a query Q prime, and I simply add more atoms. I add more atoms to it, and I call the new query Q. Then I always have a homomorphism from Q prime to Q, which maps the same variables to themselves. And then, every atom from here would be mapped to the same atom over there. It's just that Q has more atoms. So your observation is right on. In some sense, Q is adds more conditions. Yes.
Why am I allowed to map constants to variables and variables to constants?
We cannot map constants to variables.
Okay.
It's just if you think about how can you write this quickly, this is the shortest way I could write it. But the constant have to be mapped to constants. And when I write this, when I say H of a tuple, I mean here that this tuple might contain variables or constants, and I want H to be defined on constants as well. Let's see an example. The best usage of a homomorphism is to explain what a query answer is. So the answer of a query on a database consists of finding all homomorphisms from the query into the database and returning the image of the head variables of Q. So this is a mouthful, so let's go over it. Here is a query. And notice that we have variables x, y, and I also have a constant a. So what does this query do? It says return all the x's, all the values x, for which x is in the relation R, and there exists everything, every variable that's not in the head is essentially quantified. So, and there exists some y such that x and y is in S, and the same y is in T together with a constant a. Okay, so here is a database. And again, I can think about this database as a query, as another query, it doesn't matter. So in order to evaluate the query, what we are going to do, we are going to look for a homomorphism from Q into the database. So the homomorphism must map the variables x and y and the constant to variables and constants. So I wrote all possible homomorphisms like this. So here are the three variables and constants. They come from Q. And they need to be mapped to the constants in the database. There are no variables here, just constants. So the first line is one homomorphism. It maps x to 1, y to 10, a to a. You see, a must be mapped to a. There is no other choice. So why is this a homomorphism? What do we need to check? We need to check that R of x is mapped to something that is on the right. Is it mapped to something on the right? Yeah, because x is mapped to 1. And indeed, R of 1 is in here. And similarly, 1 and 10 exist here. There it is. Yeah, and similarly, 10 and a must be over there, so it's here. So we list all homomorphisms. There are just 3. If you try to map the variables in a different way, you do not get a homomorphism. And then we just retain the values, the images of the head variable. And this is the answer to the query. Well, so it's just 1 and 2. Yes.
What is an image?
The image is you apply the function, and what's the function return? That is the image. And often you refer to the image as you apply the function to an entire set. And then the image is a set of values. That is the image of the function. Yes?
Couldn't a homomorphism also map x to x, for example?
A homomorphism can map x to x. And the example we played on the previous slide when your colleague suggested that, if you imagine a query, and now you add more atoms, there exists a homomorphism from the original query to this inflated query that map the variables to themselves.
But like, would that be part of the results here? Like, could it map Q to itself, and then would that be also the image?
Well, you need to map the variables. So what happens if I map x to x? And I map y to y? Is that the homomorphism?
Oh, but it's not a homomorphism to the database, right?
Exactly. It might be a homomorphism, but to something else that I don't care about. We care about a homomorphism to this database, and x itself is not here. We only have 1 and 2. Yeah, that's all about homomorphism. Yes.
So when I create a homomorphism to the database, I'm allowed to substitute like elements in the domain. I can map variables to elements in the domain of the database.
Yes.
Okay.
And this is why here, where we say that we can map the variables to constants. So if Q is a database instead of a query, then it only has constants. So we have to map the variables to constants. Yeah, so at the risk of confusing you, I try to write the definition as general as possible. So now we have everything. Good. So that's a homomorphism. It is a very simple concept, and once you get familiar with it, basically. You look confused. Do you have any questions?
No, I didn't. So, in what situation would you be interested in the homomorphism to another query rather than to a database? Like in those situations, you're just like substituting different terms for the existing variables?
It's a good question. So, but this slide suggests that we need homomorphism in order to evaluate queries. But the homomorphism goes from a query to a database. When do we ever need homomorphism from a query to another query? And the answer is here, when we talk about containment. And I think we briefly mentioned this last time. If you have a homomorphism from Q prime to another query Q, then every answer that Q returns on some database is also returned by Q prime. And moreover, this is a necessary and sufficient condition. Pretty cool. This is how you can check if two queries are contained, and then you check the opposite direction and you have checked that they are equivalent. That's a topic for Thursday. Yeah, so this is why we care about homomorphism also between queries and between queries and databases. Okay, but now I want to do query evaluation. I want to ask a question. What is the complexity of finding such a homomorphism or listing all the homomorphisms? And it's not hard to see that not just for conjunctive queries, but even for unions of conjunctive queries, the combined complexity of query evaluation is in NP. So remember, to prove that it's in NP, all we need to show is that if we can guess the right thing, then we can check in polynomial time if that guess is correct. So start with a union of conjunctive queries. I'm going to assume that this is a Boolean query. So this union of conjunctive queries is really the disjunction of Boolean conjunctive queries. When is this disjunction true in a database? What do we need to check that in a given database Q is true? Well, one of these has to be true. Just guess which one is true. Qi. We're going to guess Qi. Now we need to check that Qi is true. And Qi is true if there exists a homomorphism from its variables and constants into the database. Then it is true. So we just need to check the Qi, which is quite easy. We could actually enumerate over them. This doesn't require NP. But the homomorphisms, we cannot enumerate them. In general, there can be exponentially many. But in the complexity class NP, you are allowed to guess. And this makes this places the combined complexity of query evaluation in NP. But could it be in polynomial time? Could query evaluation be in polynomial time? If we want to prove it's not, what should we prove? Yes?
Could you do something like FreeSat or?
Completeness. We need to prove that the query evaluation problem is NP-complete, that it is as hard as any NP problem. And that is our best evidence that it is hard. And you know, with the theory, nobody has proven that P is different from NP, but for all we know, we believe that they are different. So this is the next step. Let's prove that not just the combined complexity, but even the expression complexity is NP hard. What I mean by this, that there exists one database, one single database, for which the problem, given a conjunctive query, check if that conjunctive query is true on this database. This problem is NP hard. We know it is an NP because all we need to do is to check homomorphism. We are going to prove that it is NP hard by reduction from FreeSat. Yes, FreeSat is kind of our poster child of NP hardness.
On
Yes.
the previous slide, why was it sufficient to find a single homomorphism? Because earlier when you showed query evaluation, we had to know the set of all homomorphisms.
You pay a lot of attention. Very nice. So why is it sufficient to find a single homomorphism? Because here I forgot to write on the slide, I'm assuming these queries are Boolean queries. If they are Boolean, we only care whether there exists a homomorphism or there is none. If we have head variables, then we have to enumerate them. And then these complexity classes, NP, P space, they refer to decision problems, to problems whose answer is yes or no. When we have to enumerate, it gets a little bit more messy to talk about the complexity. Yeah, so now we want to prove hardness. So what we are going to do, we are going to design a single database. It's pretty small, such that for any 3-SAT problem, so such that we can reduce 3-SAT to the query evaluation problem on that particular database. Yeah, so concretely, for the database will be fixed a priori, but I'm going to describe it later, so don't be confused. The database can be designed without us having to look at the formula. Once we have the formula, we are going to design a conjunctive query that is as big as a formula. It's going to be a big one, such that the original Boolean formula, the 3CNF formula, is satisfiable if and only if there exists a homomorphism from this query into the database. And the construction is so clear and intuitive that we want to go over it in detail. So let's see the details. So this is what we want to prove, that we can construct a conjunctive query that depends on the Boolean formula, such that the Boolean formula is satisfiable if and only if there exists a homomorphism. So I will describe the database in a second. Let me first show you how the query looks like. The query looks like this. We have four relations, A, B, C, and D. Just 4 names for the relations, A, B, C, and D. Now you examine the 3CNF formula phi and take any clause C in phi. If this clause has only 3 positive Boolean variables, then we place in our Boolean query, it's the atom, A of logical variables that correspond in one-to-one to these Boolean variables. So I wrote them with lowercase, but we will have as many logical variables in the conjunctive query as we had Boolean variables in the Boolean formula. Okay, if we have 1 negation, I'm going to call it B. If we have 2 or 3 negations, I'm going to call that atom C or D. What happens if I have not Ci or, not Xi or Xj or Xk? What do I do with that clause? We just rearrange it. So just for frugality, we only need 4. Because you can arrange them and put a negation at the end, so you have fewer cases to worry about. Okay, so this is the query, not clear yet what we do with it, but now I'm going to describe the database. The database will consist of 4 tables, A, B, C, and D. And these tables, they will only have the constant 0 and 1. Several tuples with the constant 0 and 1. Here is A. It has the constant 0, the tuple 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. Here is B. Now my question to you is, how do these tables look like? Which tuple is missing from A? Remember, A must kind of encode the fact that we are looking to satisfy this clause. Yes?
Can I drop the tuple as false?
Perfect. This is the best way to say it. We drop exactly the tuple that is false, that makes this clause false, and that tuple is 0, 0, 0. Which tuple do we drop from B? Which combination makes this false?
0, 0, 1.
0, 0, 1. Here it is. 0, 1, 0, 0, no, 0, 1, 1. Yeah, so you get the idea. Very simple. No, it's quite straightforward. I don't think we need to justify it too much. If phi is satisfiable, if there is an assignment of 0 1s to these variables that makes all the clauses true, then we just convert that into a homomorphism, and that will map the query to our database. And conversely, if we have a homomorphism, from that we read as satisfying assignments. Beautiful, beautiful construction. Any questions about it? Okay, good. So the combined complexity, the expression complexity of evaluating conjunctive queries is NP-hard. Now let's go back to first of the logic. The data complexity was EC0, that's good. But what is the expression complexity? And to remind you, the naive algorithm that we described for first of the logic has this nested loop. So if you have quantifiers for all x exists y for all z, you just iterate for all x in blah, for exists y in blah, and so on. And if the query were fixed, then these loops they take n to the power k, but k is a number of variables, so it's polynomial time. But if the query varies, we don't know. Then it's more complicated. Well, it turns out that the combined complexity of FO, first of all, it is in P space. Why is it in P space? If you think about that nested loop, you only need polynomially many variables for the nested loop. So it's a matter of bookkeeping how to do those loops, which might take forever, but you only need polynomial time to represent the state of those loops. So the combined complexity is always in polynomial space. And it turns out that it is actually P-space complete. The expression complexity of FO is P-space complete. More precisely, there exists a fixed database for which the problem given a first order logic query to check if that query is from this database is hard for P-space. Which begs the question, what is a typical P-space hard problem that you know? Okay, I only know one. It's very simple. So it is the quantified Boolean formula. I'm going to write here, and you'll get the idea very, very quickly. So here is a typical satisfiability problem. Let's please up. It is x or y or not z, and I'm going to put it here because I'm running out of room. Not x or not y or z. Yeah, it is a Boolean formula. It's in 3CNF, and the question is, do there exist assignments of the variables x, y, and z for which all the clauses are true? Do there exist assignments of the variables x, y, and z? I'm going to be rigorous and write this as a prefix by saying, does there exist x, exist y, and exist z? This is the standard satisfiability assignment. The new problem called quantified Boolean formula or QBF also has a 3CNF formula, but the quantifiers you can place at the head, they can be any quantifiers. They can look like this. For all x, there exists y, for all z. And now you list here your favorite 3CNF formula. So the QBF formula, the quantified Boolean formula question is, given such a quantified 3CNF formula, is it true? I don't need to say satisfiable because it's like a sentence. It's either true or false. Notice that it's much harder. It doesn't suffice to just guess. But now you need to check that for x, both 0 and 1. There exists y, and that y might depend on x, and so on. It's a harder problem. However, it is in polynomial space. You only need polynomial space because you have polynomially many variables. You just need so much space to keep track of their values. You iterate over all these assignments, and you can check the formula. And it turns out it is p-space complete. That is a typical problem that you need to remember. So how do we prove that our problem, the expression complexity of the logic is p-space complete? Very simple. We just use exactly the same construction as above, the same. So we start. Sorry, we start from a quantified Boolean formula, which is this phi, but now there are quantifiers in front of it. And quantifiers, they are traditionally written with Q. They are not queries, they are exist or for all. So I had to write Q there. Don't confuse them with queries. And how do we reduce this problem to the query evaluation problem in FO? Well, we simply construct the same conjunctive query as before. No negation, no disjunction, just a conjunctive query. But what we do now, we don't put the existential quantifiers in front, we put exactly the quantifiers that we get from the QPF. Okay, so what did I do wrong? Yeah, and that's the end of the proof. I think it's the end, yeah. It's an amazingly simple proof, and it just reuses the same construction. Okay, so at this point, I wanted to have a discussion. How many people here are familiar with the constraint satisfaction problem? Oh, everybody, good. So then let's have this discussion. So the constraint satisfaction problem is kind of the inner working of NP plus. And it turns out that constraint satisfaction is the same as conjunctive query evaluation in a very deep and profound way. So constraint satisfaction defined in the modern version of this, I took it from this paper as a famous one by Kolaitis and Balti. A constraint satisfaction problem consists of specifying two classes of finite structures A and B. Any of them can be a singleton. And then the constraint satisfaction problem from AB is the following. We are given two structures, A and B and B. Check if there exists a homomorphism. I'm pretty sure you don't recognize it like this. Yeah, so let me give you some examples. So let's suppose we want to check three colorability. Given a graph, check if it has if it can be colored by three colors. So given a graph, check if it can be colored by three colors. What should be my structure A and structure B? Don't worry yet about the classes. How can I check three colorability? By simply looking for a homomorphism between two graphs. Let me draw for you the first graph so you can see where I'm heading. So the graph is undirected, which is it's a little bit of a complication, but no idea if this is three color. Okay. So we want to see if this is, does everybody know what three colorability means? Now we need to use three colors and make sure that no edge is colored with the same color as both ends. So I'm looking for these for a three coloring, but I want to make it equivalent to finding a homomorphism. A homomorphism is going to what?
Like three isolated nodes or something?
Three nodes should be isolated. If they are isolated, there is no homomorphism.
Any subgroups?
What do you want to put here?
Should we not edges to something? Because it's like it seems like the edges are the constraints.
Yes, it's just a triangle. Yeah, so call this node red, call this node green, call this node blue. So now if I have a homomorphism maps nodes to nodes, and it is required to ensure that every edge is mapped to an edge. So all the nodes that are mapped to red will be colored red, all those that are mapped to green, and so on. And if it's not three colorable, then there is no homomorphism. So it's if and only if. How can I model speed colorability as a query evaluation for a fixed database? What should the database be? Yes,
A relation, that expresses the edges, and then values inside of the pod.
perfect. This is by database. It's a relation, let's call it E. It has, I don't know, two attributes. And it consists of three nodes, from 1, 2 to 3, and 3, 1. Well, it's undirected, so you will also have to add 2, 1, and 3, 2, and 1, 3, because we need to put it in both ways. Notice the database is fixed. What is a query? Well, we are given a graph. From this graph, we construct a query by simply listing all the edges. So the query will be EXY, if this is X, this is Y, and EYZ, if this is called Z, and so on. You just list all the edges in the graph. So speed colorability is equivalent to query evaluation, with query evaluation of a Boolean conjunctive query on a fixed database. This is a very profound observation. Let's see if I can. In constraint satisfaction, usually the structure B is fixed. Think about three colorability. B is just that little triangle. Think about 3 SAT. B is a database consisting of those 4 iterations that we had before. So B is fixed. And usually the complexity is described in terms of the structure A, which can be any structure. Sometimes it is restricted. And this is the constraint satisfaction problem. In databases, it's the opposite. In databases, A is fixed. A is our query. And the input is B. B is a database, and that is fixed. This is why we say that query evaluation is constraint satisfaction from the other side. It's from the constraint satisfaction on the right-hand side, while the traditional constraint satisfaction is on the left-hand side. Okay, so this is all I wanted to spend here. Just for your quick exercise, try to describe Hamiltonian paths as such a homomorphism finding problem. Good. So a quick summary about query evaluation. So we still have half an hour. We need to. I still want to cover basically queries. So evaluating a conjunctive query is the same as finding or searching for a homomorphism. This problem is in NP because we need to find if such a homomorphism exists. In fact, if you think about the fact that 3 SAT is expressible here, is kind of almost a definition of NP. But in databases, we usually fix the query. And then the problem is in polynomial time, it's even an AC0. So the data complexity, which is what we really care about, is much lower. It's only when the query itself grows forever that the problem becomes involved. What I want to do next is to dig a little bit deeper into data complexity. And we will continue this in 2 weeks. When I invited Hans to give a talk on the state-of-the-art algorithm for evaluating conjunctive queries, which is the so-called 4-phase optimal join algorithm, which has the best, probably best complexity in terms of data complexity. But before we go there, I want to discuss a classic result, Yannakakis algorithm, on evaluating a cyclic conjunctive queries. Yes, Connor.
Could you talk about the implications of this, like that we have very low data complexity but high query complexity, or in real life, do very long queries occur.
Yeah, I'm pretty sure you have something on your mind, so what you would like to, because it's indeed something that requires a discussion. We have this asymmetry that the data can grow and we know how to handle it. We add indexes, we parallelize it, but if the query grows, we are in trouble. So, do you have any thoughts on this?
It seems great if the queries are short, like, are there other kind of classes of applications where we see impractically long queries?
Yeah, I can tell you the anecdotes that I know. So Postgres, which I strongly recommend to have on your laptop and to use for on daily basis, only optimizes queries up to, I've heard 20 joins or maybe just 12. Apparently it's a parameter setting. Marini knows this much better than I know. So here we go. So Postgres essentially gives up on query optimization if your query is too big. There are recent research papers that I mentioned, I think last time, that look at optimizing queries with hundreds of joins. They go way beyond what we can do efficiently. So they have all sorts of heuristics. They're pretty cleverish, but they don't get very deep. What can you do? It's an anti-hard problem to evaluate that query. And I think this is where we are. I don't think we have a good solution for evaluating huge queries. And there is a need for this. You might wonder, SQL queries are typically written by data analysts. I heard the horror stories of, SQL queries that spans 4, 5, 6 pages. Some data analysts do this, but even that doesn't take you to hundreds of queries. How do you get to hundreds of queries? And this story, actually, the first paper published on this was motivated by Tableau, this company that offers a service for visualizing data, and you get the data by writing SQL queries. What happens in the relational databases is that we define views. A view is a conjunctive query. It might compute some aggregate on the side, and you keep it virtual. You do not evaluate it, but you retain the expression of that view. And later you can write a query on top of that view. At query time, you will instantiate the view, and then you have a bigger query, and this is what you execute. People often write a view over a view, and then they forget that it's the view, and they write another view on top of this view. And by the end, they want to visualize a query in Tableau. This query actually might expand into hundreds of joins, because people forgot that this table is not a base table, but it is defined by a view, and what comes out is a humongous query. So yeah, we do have to worry, Connor, so thank you for bringing this up. We do have to worry about huge queries, but this is what theory tells us. When the queries grow unlimited, then the problem is amplified. And it doesn't mean it's necessarily hard, but it's much harder than standard query evaluation. So let's talk about standard query evaluation. And the standard query evaluation starts by observing that acyclic queries are very easy to evaluate. How many people here know Yannakakis algorithm? Okay, only a non-database person, only math. Very good. So that's my goal, to discuss Yannakakis algorithm. So now we are going to look deeper into the runtime of an evaluation algorithm for a conjunctive query. So remember that if the database is D, then we look at the active domain of D, all the constants in D, and I'm going to denote with N the total number of constants that we have in the database. And sometimes it's useful to look at the largest relation, and I'm going to denote that with M. Think about M as the number of edges and N number of nodes, something like this. So how do we evaluate a conjunctive query? Well, a naive way is to use nested loops over the domain. Just iterate for each variable in your query, iterate over the domain, and at the end, check everything. This runs in time, which is n to the power the number of variables. It's polynomial time. but can we do better? Database systems, they compute one join at a time. They join R1 with R2, and then they join this, this should be R3, and so on, and they join this with all the relations. So this gives us a runtime, which is the product of the sizes of the relation is what we get, because each join doesn't take longer than the product of the two sizes. In order to compute a join, you need to sort them. You need to sort the two relations, and then you can compute the join. So you need an extra log and factor when you do the join, and this is why I'm going to put here a tilde to mean a log and factor. We don't like these runtimes. The runtime we would like is the size of the input plus the size of the output. That is kind of ideal. You can't do better than this. You just have to read the input, no choice, and you have to read the output, no choice. That is our ideal time. And there are two techniques that can sometimes lead us here, but not for every query, only for some queries. And the two techniques are semi-join reduction combined with tree decomposition of the query when that is possible. Okay, so ignore the blue part, because we talk about the details. So semi-join reduction. We discussed the joins. It's one of the fundamentals, the 5 fundamental operations in the relational algebra. You can think of a join as a very simple full conjunctive query. The join of A and B simply, it's returned. It's what you see here. I don't know how to create that. This is the join of A and B. The semi-join is interesting. The semi-join is asymmetric and returns only the variables in A. So the semi-join is a subset of A consisting of all the tuples that join with something in B. It's a very important operation in database systems. It's denoted with this half of a join. It's like a join, but without that part. That is a semi-join. Computing a join can be done in time which is linear in A and B plus this logarithmic factor. You just need to sort A and B. And once it's sorted, we can iterate over them and do like a merge. And we just need to report the result of the join. So computing a single join can be done in time proportional to the input plus the output. Computing a semi-join is even cheaper. We only need to scan the inputs because the output is guaranteed to be a subset of the relation A. Yes,
So how do things like factorized representations come into play here? Because I think I can imagine a representation of your join such that you compute the full join in the same, computing the full join and the semi-join are basically the same thing. You just defer the Cartesian product of stuff that you don't have to do until later.
Yeah.
So
I think this comes on the next slide, but we're heading. So clearly the semi-join is a step towards completing the join. How far did we get here? I think this is where you're sure. Yes.
I'm curious if the reason we use it always with tilde is because it's usually stored ahead of time. And so in practical terms, you don't usually use or is it just stored and
Yeah, so the question is, do we really need the tilde? Maybe we can sort the relations ahead of time, they're already sorted, and then we are in good shape. And it's a long story in systems-wise. You can pre-sort them, but then if you join on the wrong variable, then it's no longer sorted. For example, suppose we also want to join a B with C, but now the join is on the attribute Z, no longer on the attribute X. So then we need to resort. The original system that first implemented query optimization, system R, keeps track of the partial sorting, because sometimes you have to sort at one time, but you don't want to sort a second time. So they called, so inside the syntactic representation of a query plan, they identify interesting sorting orders. It's called interesting orders or interesting sorting orders. They just keep track of, if I reach this part of the plan, then this relation is sorted, that relation is not sorted, something like this. So it's very important to keep track of these sortings if you don't want to sort the second time. But for our purpose, I'm completely going to ignore this. I'm going to assume that you can always sort for free. Okay, good. So this is what I wanted to say so far. A join can be computed in time proportional to input plus output. The same join just proportional to the input. That's all we need. So how do we use this? My goal is to show you Yannaka's algorithm. It usually does not require so much preparation. However, there is a subtle proof of Yannaka's algorithm. And usually this is done using a little bit of hand waving. It's not that hard to prove it. But database systems, they don't understand hand waving. They need optimization rules. They need algebraic rules to prove that this query is equivalent to that query. And Max here, he is the expert in these rules. There is this beautiful system called EGG that Max essentially developed at the University of Washington. And EGG is like, the ideal toy for a database optimizer person, because all these read-write systems that exist in database systems, they are proprietary. You cannot get to the read-write system used by SQL Server, which has about 500 rules. The Postgres read-write system is hard-coded in C++. You can't really use that either. So now with EGG, we actually have an open source tool to experiment with read-write systems and experiment with query optimizers. This motivates me from being quite rigorous about the Yannaka's algorithm and trying to identify what are the identities that we need in order to guarantee that Yannaka's algorithm is correct. Okay, so let's see them. Here are some of them. First, this is unfortunately not an identity, but it's obvious to observe that the semi-join of A and B is a subset of A. Okay, so if the important consequence is once you replace A with a semi-join, its size does not increase. It can only decrease. We're going to do this a lot. Replace A with a semi-join. After you replace A with a semi-join, if you do the join now, it's the same answer as doing the join before. It's like an idempotent, if you want. The semi-join is the same as doing the join and then projecting on the variables of A. It's also a useful thing to do. Okay, so if you do a semi-join a second time, nothing happens. It's like idempotence. Here is a question for you. Suppose I want to semi-join A with the result of joining B and C. Can I just semi-join A with B and then semi-join again on C? No, but there is a simple condition, a syntactic condition under which this falls. It's a little bit subtle to use. I'm going to show this to you, and then maybe this happens if A and C, if all the variables that say share are part of B. Okay, so in that case, you know what? Actually, I have some doubts now. I'm not completely sure if it's correct. Let's put it aside. So the design process of these rules, they're not going to work from day one. I have some doubts about this. Here is a simple one. I have no doubts about this. If A and B have the same attributes, then what is the same? Intersection. Beautiful. Then the semi-join in either direction is just intersection. And I have another one. when can we say this? And I think this, again, this is correct. So I want to semi-join A with B, semi-join C. And I claim that this should be equal to semi-joining on B, semi-joining on C, and then taking the intersection. But it doesn't always hold. And for this to hold, we need to check that B and C do not share all the variables that they share when we do the join. All these variables are already part of A. And if this holds, then it means that whatever B and C do here, we can observe by semi-joining separately on B and C. Let's put it negatively. If B and C share the variables that A does not have, then this join might reduce their sizes based on that join variable. And we lose this information when we do the intersection. Okay, I think what you should take out of this is that these identities are actually not that easy. They're quite subtle. So if you want to play with egg, which I strongly encourage you, and Max is here, so you can ask him anytime. If you want to play with egg, these are super important things. You get them wrong, and you get ridiculous identities. Good. So let's talk about how the queries need to look like to be able to run Yannakaki's algorithm. A query needs to be acyclic. A conjunctive query is acyclic if it admits a joint tree, which is a tree with two properties. The nodes of T are in one-to-one correspondence with the atoms of T. And second is called the running intersection property, which says for any variable of the query, the set of tree nodes that contain that variable form a connected component. This is standard in 3D compositions of graphs. How many people here know 3D compositions of graphs? Okay, not that many. So here is an example. It's a query, don't look too deep. Here is a joint tree of the same query. Notice that I place the atoms on a tree. No big deal. But now we need to check the running intersection property. We need to check this for every variable. I picked variable y, and sure enough, if you look at y, the atoms, the tree nodes that contain y are connected. Here is a non-example. This is a triangle query. AXY, BYZ, CZX. It's a triangle, so there is a cycle. Why is this not acyclic? Why can't I just place A followed by B followed by C, and I have a chain?
You'll have broken one pair.
Then I have broken the running intersection property for which variable? If I place them in this order ABC,
X.
the X, because X occurs here and here, but does not occur in the middle. That is a super important property for Yannakaki's algorithm to work. Okay, there is a famous algorithm for checking if a query is acyclic, and in general it's a hypergraph is acyclic. It's called the GYO test. And it goes as follows. Find a variable that is isolated, which means it only occurs in a single atom. If you find such a variable, you can simply remove it, and that atom will have one less variables. Or if you can't find it, find an ear, which is an atom that has only variables that are already present in another atom. By the way, this is how you distinguish between people with accent and people without accents. Try to express the difference between year and the year 2023. I can't do this. Yeah. So I'm referring to an year. So for example, this query, how do we check using the, by the way, if the query is acyclic, if the result is in empty, we're going to remove everything. How do we check this? Which variable is an year?
Yes.
X.
Okay.
X2, yeah, but my slide say X. Okay, so here we're going to remove X. Here it is, it's gone. X is gone. So now we could remove S as well, but I didn't do this. I looked for an year. Here, which atom is an year? A, because it is contained in B, the next one. So you remove it and you continue like this until you have removed everything. But with a single variable, once you remove this, then you're left with nothing, and the query is acyclic. If you get stuck, the query is not acyclic, you cannot run Yanakaki's algorithm as given. Now this is a GYO test for acyclicity of a hypergraph or of a query. Cool. So let's see Yanakaki's algorithm. First, for the simpler case of a Boolean conjunctive query. So we just check, Boolean means all the variables are essentially quantified, and we want to compute a query in time which is linear as the size of the input. I should put a tilde here, I forgot to put a tilde. How big is the output for a Boolean conjunctive query? It's 1. It's either true or false. It's constant or it's 1. So this is why I did not include it here. So here's how it goes. We are simply going to, instead of computing the join and then checking if it's empty or non-empty, we are going to do semi-join reductions. So for this particular query, which is acyclic, we are looking at a tree, and we are going to do a semi-join reduction bottom up in the tree. So it goes like this. Start from the leaves are, you leave them, semi-join reduce D using E. Yeah, so D now only contains tuples that we join with E. Then semi-join reduce B with C, same thing, so B now is smaller. It only contains tuples that we join with C. Then repeat this with D. So it means that B will contain only tuples that join with those tuples in D that join with E. And at the end, we semi-join A with B, and if the result is non-empty, then the query is true, and if the result is empty, then the query is false. Why is this correct? This is where I'm heading with those identities. So the query is true by definition if after performing all the joins, the result is non-empty. So this is what we should have checked. If the join of everything, so A join, B join, C, and so on, if that is non-empty. But this is equivalent. This is equivalent to checking if the semi-join of A and all the joins inside are non-empty. I should point here. It's equivalent to checking if the semi-join of A and everything inside is non-empty. But what is inside? Well, inside is the rest of the joint. So it's B joined with something. But B, I mean, A and the rest, they only share variables that are common in B. So therefore, we could do the semi-join first and only semi-join A with the result of the semi-join, the most. So this is what makes this algorithm correct. Yes.
The point is that that last equality only holds if we assume the running intersection property because of the rewrite rule, like from 3 slides ago, bond rewrite rule.
Exactly.
Okay.
So this only holds because of the running intersection property. And this is why those laws, which one I'm afraid is wrong, are so important. Yeah. Good. So this is the Yanakaki's algorithm for Boolean conjunctive queries. What happened here? Okay, something is wrong. It froze. Why did you freeze? Okay. But now I want to move to the other extreme, not a Boolean conjunctive query, but a full conjunctive query. So now we don't want just yes or no. We want all tuples x, y, z, u, v, w, s that satisfies this query. And the first question is, can we just join them? Can I join A with B and the result with C and result with D and so on? With that, of course, the result will be correct. Nothing is wrong about joining them. But our goal is to compute this in this time, therefore with the parentheses. So what can go wrong if we just join these relations one after the other? Yes?
We might compute some subrelation that's really big and then discard those at the top because we have a join that discard, yeah.
Exactly. So some of the intermediate relations might be huge, but later they become empty or they become much smaller because as we continue to join, we discover that many of those tuples they don't join this thing. This is the goal of the semi-join reduction. Yeah. So if we were to, I should have shown this to you earlier. If we were to just join one at a time, so join A with B and then the result with C and then the result with D and so on. If we just join like this, some of these intermediate results, they may be much bigger than the final output. And I have an example to slide later that illustrates. It's very easy to construct such an example. So we don't want to do this because the intermediate results can be much larger. So what do you suggest? How should we do this better? Yes?
So are we, like, we could push down A into the leaves, is that idea?
Yeah, when you say push down, what operation do you have in mind?
Like distributing the join of A over, I guess there's a distributed one from a few slides ago, I forgot.
Semi-join. We're going to do a semi-join reduction. We want to reduce every relation to only those tuples that participate in the final join. This is exactly what a semi-join, what Yannakakis algorithm does. It has two phases. In the first phase, it does a semi-join reduction. And in the second phase, it computes this join in, it has to be in a particular order, but it's pretty intuitive to see in which order. So let's talk about the semi-join reduction first. It has actually two sweeps. There is a bottom up, and like what we did for the Boolean query, and that guarantees to semi-join reduce the root. But we don't know yet about the leaves. So there is a second sweep, a top-down, where we do exactly the same kind of semi-join. We replace every relation at the tree node n, and is a tree node. We replace it with the semi-join of the relation with a parent, with the relation of the parent. And then finally, we just compute all the joins in the order, has to be a particular order, top-down. And this is what we've done. And the algorithm is correct and runs in time, which is linear in the size of the input and the output. I want to show you an example, and then I have a short discussion, and then we'll stop. We are going to skip all my attempts to do the proof, which now a little bit kind of doubted. This is why I have egg. You can check this egg if my identities were correct. Okay, so a quick example. This is our query. Now we want the full answer. So the reduction, the semi-join reduction has two sweeps. One is bottom up, pretty much like we did for the Boolean query. Then there is also a top down, which ensures that the relations at the bottom are also semi-join reduced. And then finally, now we can compute the joins one at a time, and we are guaranteed that each of these relations, which is just partial, it will only have some of these variables, but we are guaranteed that each relation is part of the final output that will be produced. And since it's part of the final output, it will never exceed the size of the final output. Okay, So at this point, I wanted to bore you with lots of identities and proof of the correctness, but I'm going to skip this because I want to show you two cool things. First of all, it is really true. Can the intermediate result grow along if we don't do the semi-joint reduction? And there is a standard example, and I want to show you this. My picture is pretty ugly, but the example looks like this. We have k relations, and each relation is kind of a complete bipartite graph, but actually consists of two. So R2 has two complete bipartite graphs. Yeah, so it has many nodes here, contains all the tuples, and then there is a second copy, completely disjoint from the first one. Similarly for R3, except the first relation, it only has the complete bipartite graph for the first half, and the last relation only has a complete bipartite graph for the second half. If you compute any join, the size will be enormous because each of these relations multiplies by n the number of active domain. Yeah, multiplies by n the size of this join. But how big is a final join when we join all R1, R2, Rk? It's empty because there is no path from the left to the right. So this is a typical example. In any order you join them, you will get a huge result if you don't do a semi-joint reduction. If you do a semi-joint reduction, then you quickly discover, if you go from left to right, you quickly discover that the bottom part is useless because it was not part of R1. So you inform Rk that the bottom part is useless, but Rk says, I don't have a top part either. So when you go back, you discover that the result is empty. Good, this was one. The second thing I wanted to show you, and I still need like 3 minutes. It's a simple idea, but it can be a source of confusion. We discussed Boolean queries, and we discussed full conjunctive queries. What happens if we have something in between, in which we have some variables in the head, but also some essentially quantified variables? It turns out that in this case, we cannot always compute the query in time proportional to the input plus the output. It's really not possible. But we can do this if these output variables are such that the query is so-called acyclic free connex, which means that it remains acyclic even if we add an artificial atom that consists of all the head variables. And then, yes, then we can compute it. Okay, so I wanted to show you an example. Suppose we have the query as before, and we want the variables c and d. Where do we include these variables? Where will you put them? Where to keep the query still acyclic, you need to place the output here. This is just a test to check that this query is so-called free connex. And now this is still a tree decomposition, it's still a joint tree, but this doesn't exist, and so it's just for us to check that we can compute this query. So how do we compute it? The semi-joint reduction works as before, and when we do the joins, we just make it sure that we do the joins towards this artificial node, and we only retain the variables needed for this node. Only retain T and P. Good. So we are 3 minutes over the 10 minutes. So it's a good time to stop. Next time I will quickly review the main ideas. But next time I really want to go to query containment, which is a super fun topic. And especially with inequalities, it gets very subtle. That is actually a great test for egg, checking query equivalence under the presence of inequalities. That is a great test bed. Good, so we will stop here. The next homework is already posted. Enjoy it, and then we look at your signatures.
Yeah.